An adaptive processing system is one that dynamically adjusts its processing parameters in responses to changes in the input signal or the environment. Such systems are characterized by real-time analysis and feedback loop mechanisms. At the heart of these systems lies a powerful three-stage pipeline: feature extraction, feature processing, and signal processing, a cycle that allows AI tools to analyze, compare, and adapt their effect settings in real time. The first step is feature extraction. Here, the system receives raw audio as input and converts it into meaningful descriptors, like frequency content, spectral balance, and other musical features. These features are captured at high resolution, frame by frame, giving the system a detailed sonic fingerprint. In the second stage, feature processing, the system compares the extracted feature values from the raw audio with a set of predefined rules and constraints. To better understand what happens at this stage, let's review some of the most common constraints used in adaptive audio processors. These are audio engineering best practices, descriptors, machine learning models, and reference tracks. These best practices are drawn from decades of recording experience and mixing handbooks. For example, boosting around 5 kHz can enhance vocal presence, while 240 Hz is associated with body or boominess in instruments like voice, strings, and guitar, frequencies that may need adjustment depending on the mix. AI systems can encode these rules and apply them automatically based on detected instrument type and genre. Another form of constraint comes from descriptors. These are words that audio professionals use to describe the character of a sound, such as warm, bright, punchy, smooth, or airy. These terms have shared industry-wide meaning, each tied to measurable signal features like EQ, balance, dynamic range, or harmonic content. AI tools learn these correlations, allowing users to simply choose a descriptor such as warm or medium, and the system automatically applies the corresponding processing configuration for that sound or mastering style. Another type of constraint is powered by machine learning models trained to recognize instrument type or vocal content within each track or stem. Once identified, the system applies context-aware settings that adapt to the characteristics of the source. In this example, the bass track is automatically shaped across low to high frequencies, tightening the low end and enhancing overall clarity in the mix. The final and widely used constraint in adaptive audio processing is the reference or target track. A reference track serves as the spectral and dynamic model. The system analyzes its tonal balance, frequency distribution, and loudness curves. The current track is then automatically adjusted in EQ to match the reference tonal character, ensuring consistency of tone and feel. Users can load or save custom reference profiles, allowing the system to adapt processing toward a clearly defined target sound, a practice now essential in both mixing and mastering. So the system has compared the extracted feature values from the raw audio with a set of constraints and its corresponding rules. From this comparison, it generates parametric controls that guide the signal processing stage. In signal processing, the system applies these decisions in real time, dynamically adjusting EQ, compression, stereo width, or balance to shape the sound according to the chosen constraint or reference. This is where analysis becomes action, transforming extracted data into musical intention. When we move from single track to multi-track mixing, the challenge increases dramatically. The system must not only process each track individually, but also understand how all tracks interact in real time, a concept known as cross-adaptive processing. In an intelligent multi-track system, each track is analyzed separately to extract key features such as frequency balance, dynamics, and timbre. These features are then sent to a central cross-adaptive feature processing block, where the system evaluates the relationship between tracks. Based on this analysis, it generates control data that informs how each track should be processed in relation to the others. For example, a guitar may receive different EQ settings depending on whether it's playing solo or alongside vocals, while compression on drums may adapt dynamically to the bass track's energy. every decision is context-aware, ensuring that all elements coexist coherently in the mix.